technical expert who will take us through the components and the technology therein. So we have Mr. Murlidhar Phatak from Siemens. So Mr. Murli is an experienced professional with over 30 years experience in business development, project execution and acquisition, servicing and commissioning. He is working as a senior business development manager in the automotive vertical at Digital Industries in Siemens India. He works with close collaboration with the bus manufacturers in India and the Siemens manufacturing units to roll out the Siemens portfolio of solutions in the EV segment. He has extensive experience in analyzing project requirements and rendering technical guidance to the clients. His expertise areas include traction drives, motors, PEM-based electrolyzer for hydrogen generation, automation, CNC controls and drives, and DC and AC drive. So without spending much time, I would now like to invite Mr. Murlidhar Phatak for taking us through the technical aspects of EV design.
Thank you, Dhruv, for the introduction. Good afternoon, everybody. And thanks to GreenTree and other organizers for giving me an opportunity.
There is a slight audio fade out. Maybe you can recheck if the connection is stable.
Can you hear me?
Yes. Now I can.
Okay. So what I said, I'll just repeat. Thank you for the good introduction, and thank you GreenTree and other organizers for giving me an opportunity to discuss about electric mobility with you all. So is my screen visible?
Yes, it's visible.
Okay. So with good background set by the try to take the session a little bit forward, and the overall presentation is divided into 5 modules. The first one gives basic understanding about electric vehicle design. The second one talks about drivetrain of electric vehicles and the types of drivetrains. The third module talks about motors, different types of motors such as Bldc motors, induction motors, and Pms motors, etc. The fourth module talks about battery design and what is meant by battery management system. And the fifth and the last module talks about the charging solutions. So this is an overview of how our discussions would flow. So let us move on to the first section, that is the basics of our electric design. On screen, this is a generalized block diagram of an electric vehicle. The number of boxes and the descriptions might change here and there depending upon the type of vehicle. For example, a block diagram of a two-wheeler would look somewhat different. Block diagram of three-wheeler would look somewhat different. Could be a subset of this block diagram, but in a generally speaking, these are the constituent components of an electric vehicle. And in the next slide, I have tried to add some description with respect to each box to make it more clear. So let us move on to the next slide. So the most important part of the electric vehicle is vehicle controller. So vehicle controller is also abbreviated as VCU, or sometimes it is also called as EVCU, that is electric vehicle control unit. And this is basically heart of the entire electric vehicle, which takes care of monitoring and control functions on a vehicle level. So the individual monitoring and control units, for example, the energy management unit for the battery section or auxiliary power supply, then electric power converter, all these individual units do their control and monitoring functions on the local level. But finally, all the control signals as well as data is passed on to the vehicle controller to do corrective actions at a vehicle level. So VCU is the central control unit, and it is generally mounted somewhere near the driver's desk, generally speaking. Second is, I will turn on my cursor so that yeah. So second part is energy management unit. Energy management unit is actually it is an interface between the energy source and the vehicle control unit. And energy management unit function is basically to take care of the charging profile of the battery. For example, each battery has got its own charging characteristic, which is dependent upon the type of battery which is used. So the energy management unit takes care that the charging of the battery happens in that particular manner, which is as per the charging characteristics of the curve. And it also communicates the data from the battery, such as health of the battery in terms of battery temperature. Then what is the, if it is a air cooled, if it is a water cooled battery, then what is the temperature of the coolant, what is the rate at which the coolant is flowing, etc. So all this information is passed on, and also the available charge which is there in the battery. So all this data is passed on to the vehicle control unit through the energy management unit. Over here you see there are three symbols used. The two parallel lines over here, they indicate a mechanical linkage between components. Black arrow, bold arrow, it indicates electrical linkage between components, and a single arrow indicates the control link. So these all symbols are used within this block diagram. So as you can see that there is a bus linkage between energy management unit and the vehicle control unit. Similarly, there is a bus linkage between energy source and the energy management unit. Third part is energy refueling unit. Energy refueling unit is a general term which is used for charging the energy source. Now, energy source could be a battery, it could be a fuel cell, or it could be some other energy source. But the mechanism or the device which is used for, in case it is a battery, we call it as a charging unit. For charging, the device which is used is called as energy refueling unit. And it is basically, it takes care of the charging of the energy source. Next comes the auxiliary power supply. In a electric vehicle, apart from the main traction power or motive power, there are other power requirements as well. For example, the power which is required for air compressor in the air conditioner, or auxiliary power required for the lighting system, or maybe pneumatic controller or something. So all these auxiliary powers are summed up together, and a suitable auxiliary power supply is chosen, which is kept separate from the main traction controller. And this auxiliary power supply unit basically is responsible for generation of all those auxiliary power supplies. Typically, this is a DC-DC converter. It takes power from the battery and steps down to the required DC or AC voltage levels as required for the system. In addition to that, this is a block which shows it is called an hotel climate control unit. See, basically, this takes care of the climatic conditions within an electric vehicle, basically humidity levels, temperature levels, etc. After that, there is another unit called as power steering unit. It is self-explanatory. It takes care of steering of the power steering of the vehicle. Then at the top, connected to the vehicle controller, there is a device called as electronic power converter, which is basically a traction drive, which is responsible for driving the electric motor. This is typically a four-quadrant drive because it should be capable of delivering the energy to the motor in the motoring mode, and it should be capable of taking the braking energy from the motor and put it onto the battery during regenerative braking. So this is typically an IGBT-based variable frequency drive, which is designed for traction applications. This is not a standard industrial drive, but it is a traction drive which is designed for vehicle applications. Then comes the electric motor. Electric motor is coupled to the vehicle shaft. Electric motor could be an induction motor, it could be a Pms motor, it could be Bldc motor, depending upon the type of vehicle. And electric motor gets coupled to the vehicle shaft. So in some cases, it is possible that the electric motor is capable of generating the torque required by the vehicle. In that case, there is a direct linkage between the electric motor shaft and the vehicular shaft. In some cases, a gearbox stage would be required in between the electric motor in order to step up the torque as required by the vehicle application. So that particular gearbox is symbolized as mechanical transmission. So mechanical transmission consists of this gearbox, plus it also consists of some planetary gears which are generally required when the vehicle takes a turn. The vehicle's rear wheels are to be driven at different speeds in order for the stability of the vehicle. So combination of these two types is represented by mechanical transmission. And mechanical transmission, then this is the axis on which the wheels of the vehicle are mounted. So this is an overall representation of electric vehicle. In some cases, I would just mention it briefly over here, that in some cases, those types of motors are called as hub motors, which are directly mounted on the wheels here, over here. And advantage is that basically it improves the efficiency of the vehicle, because the conversion efficiency which goes in converting this power to mechanical power, it doesn't happen. There is a direct coupling between the motor and the wheel without any gearbox in between. So such types of motors are called as hub motors. And there are certain manufacturers in the world who prefer this kind of design. And of course, those are tailor made for the vehicle applications. The next slide, this gives an overall view of what all components are used in an electric vehicle. Here it is, the electric vehicle is represented in the form of an electric bus. So over here, battery mounted. So generally, in case of depending upon type of electric vehicle, the location of battery mounting changes. For example, in case of cars, it is kept at the bottom of the vehicle to increase the stability of the vehicle. In case of electric buses, most of the times, due to the big size of the battery, it is generally mounted on the top of the bus. In some cases, due to vehicular requirements, or in some cases, the battery sizing becomes very high and it becomes difficult to accommodate the entire battery rooftop. Then what is done is the battery is distributed onto the vehicle. So it is called as distributed battery system, which means that most of the part of the battery is mounted over here. Some portion is mounted maybe on the left side or right side, and it becomes a distributed mounting mechanism. After that, this is a component which is called as generator. Actually, this is what is written over here is alpha generator, because this slide I have taken from our company's. I represent Siemens, so from my company's slide deck, and alpha stands for the product series of inverters and motors which are manufactured by Siemens. So that is why it is represented as alpha generator. So generator is present in hybrid vehicles. It is not present in electric vehicles. Then comes alpha PM motor. So over here they have shown a permanent magnet motor. However, depending upon type of vehicle, the type of motor and configuration of the motor could be different. Then here they have shown inverters. Again, these are named as alpha inverters. So basically inverters there are two types of inverters, two or three types of inverters which are used in electric vehicles. One is basically the main inverters which drive the main powertrain. Second set of inverters are present for the auxiliary power generation. And there is another inverter which is generally kept separate for driving air conditioning. So that is the third inverter which is present in an electric vehicle. I'm specifically talking about electric buses. In electric cars, there may not be so many inverters. There could be maybe only one inverter which is taking care of all these three requirements. Then there is another block over here. This is DICO. That is basically the inverter and the EVCU. That is the electronic vehicle control unit. Sometimes this particular block is mounted separately, or sometimes the hardware of this particular block is integrated inside the alpha converter. So you would see only one block and only a set of maybe one or two cables coming and getting terminated at EVCU. So this is gives an overview of the components of an electric bus, or in generally talking for an electric vehicle. So this gives an overview. This is basically a plot of vehicle driving range in kilometers on the x-axis, and sales price of the vehicles in euros, also applicable in the INR also, or any other currency. So as you would see from this diagram, let us start from 2014. In 2014, as we can see that the price of the vehicle was extremely high, and that was the time when the prototypes of these vehicles were getting developed. So obviously, during normally design stage, the costs are not known, or there is no clear-cut thought on price reduction as such. It is only the main focus is on the development of the vehicle. So the sales price, let us call it as developmental price or maybe prototype price. The price was very, very high, and also it was possible to develop vehicles in good range, maybe around somewhere between 300 to 400 kilometers. The range of the vehicles was good, but the price was very high, so they were not really suitable for series production. Series production is basically when you develop vehicle into huge quantities. That phase is known as series production. So during 2014, the vehicles were not really ready for series production. However, they developed some good prototypes. Then during the era of 2014 to 16, it was possible to bring down the cost considerably to a more or less acceptable price, at least to certain segment of the entire population. However, the range was limited to 150, maybe 150 around. Then after 2017, it was going ahead. It was a good combination of good range as well as widely acceptable price of an electric vehicle. So the real series production of vehicles, electric vehicles, started beyond 2017. And also all these things are government driven, because there are many subsidies, which are many announcements which are made from individual governments of those particular countries. So electric mobility is basically government driven by government policies, government subsidies, government norms and regulations, to make it very clear. Okay, this particular slide summarizes what I said in a different way. Basically, electric vehicle over here, it is represented by a four-wheeler, that is a car, and major parts are shown as electric propulsion, energy source, and auxiliary system, which we already talked about. Electric propulsion consists of electric motor, then controller, power converter, mechanical transmission, and the driving wheels. Energy source comprises of an energy storage, which could be a battery, it could be a fuel cell, it could be an ultra capacitor, and a battery management system and battery charger. Over here, I would like to mention that battery chargers are of two types. In certain types of vehicles, there is a provision for the battery getting charged on board. So that means the charging mechanism is basically on the vehicle itself. In that case, it is known as onboard charger. And in some vehicles, especially bigger vehicles, there is no onboard charging mechanism. So the charging happens at charging depots, which are placed either en route or at the start and at the end of the route. So such type of chargers are known as off-board chargers, because those are not present on the vehicle itself. They are off-board. And the third one is auxiliary system, which consists of power steering unit, temperature control unit, and auxiliary power supply. So this ends our first module, which talked about basics of electric vehicle design. Now let us enter into different types of EV drivetrains. Okay, so the first slide again talks about main blocks of an electric vehicle. So over here, this is a battery. battery pack, then onboard charger, because in this type of vehicle which is shown over here, there is a provision for the charging to happen on board. So this is an onboard charger. However, as shown in the diagram, this onboard charger needs an external power supply. So this is not really an onboard charger. It needs help from outside. So this is probably a plug-in kind of, not a hybrid vehicle, but plug-in electric vehicle, maybe we can say. Then there is a DC to AC, or maybe in simpler language, inverter, which inverts the power coming from the battery and it feeds to the electric motor. Electric motor through a transmission feeds the wheels. Okay, and as compared to the component count of an electric vehicle, we can say that around 60% of the components are lesser as compared to IC engine. Whereas whether there is a significant reduction in weight or not is a point of debate, because even though we are removing the IC engine and the associated mechanical components, we are adding battery weight to it. So there is a kind of compromise comparison between weight with IC and weight without IC. So there may not be a significant reduction in weight when we convert it to an electric vehicle. However, the number of components and the number of complications are reduced to an extent. Now, let us try to see what is a hybrid vehicle and what is an electric vehicle in this particular page. So on the left hand side, you would see that there are 5 elements written. First is the internal combustion engine. Second is electric motor. Third is power electronics. Then the high voltage battery and the charging contact for the external battery. Now, the first diagram is of fully hybrid HEV. HEV stands for hybrid electric vehicle. So hybrid means basically there is no single source which drives the vehicular shaft. There are more than one sources. Typically, a combination of internal combustion engine and maybe a fuel cell, or internal combustion engine and a battery pack, something like that. So similarly, over here it shows internal combustion engine and a battery pack. These are the two energies. Then a motor, and then this is the battery pack. What is absent in this block is charging contact for the external battery, which means that the charging happens on board itself completely. So in this type of vehicle, there is no provision of charging the vehicle from outside world. So as you can see in this block diagram, the gasoline engine is capable of charging the battery. How it charges the battery, I will show in the next slides. And so in the second block, now here it is very similar to the first one. The only difference is this last block. It has got a provision for charging the battery from an external source. So that is why it is called as, since we are plugging in from an external source, it is known as plug-in hybrid vehicle, or PHEV. And in the last block is for electric vehicles. As you can see from here, there is no gasoline engine present in this case. There are only 2 blocks. One is the electric motor. What should also be shown over here is an DC to DC to AC converter and the battery pack. So if you compare these 3 top views, you can see that the battery capacity is almost the same in these 2 cases, but there is a significant rise in the battery capacity in this case, because in this case it is a fully electric vehicle, and all the electric power, all the motive power which is required for driving the vehicle comes from battery. So that is why the battery size is higher over here in the last case. So in the next slide, we will try to explain the different types of hybrid electric vehicles. Actually, I will tell you the reason behind development of hybrid electric vehicles. Basically, this technology of electric mobility is not new. the components of electric mobility were developed much before. However, this technology could not take off in the beginning because the required charging infrastructure was not completely ready. So that is why a technology which was somewhat intermediate to a fully electric vehicle and a fully gasoline driven vehicle was developed, wherein a provision was still kept to drive a vehicle with a gasoline engine in case electricity fails. So such a vehicle which has got a combination of two sources was termed as hybrid electric vehicles. Nowadays we see that cars or two-wheelers or auto rickshaws, other three-wheelers are completely electric. However, also electric buses, they are completely electric nowadays. However, in case of certain off-road vehicles and also in long-range trucks, this hybrid mechanism still exists, because when a vehicle has to run over a long route with thousands and thousands of kilometers to go, and if there are no charging stations available at different points at sufficient number of stations, then you need to propel the vehicle continuously, irrespective of whether energy is available from battery or not. So in such cases, especially for highway trucks, this particular mechanism still exists. So this hybrid electric vehicle, I have mentioned some commonly known variants. First is diesel hybrid vehicle. When a vehicle is driven with the help of a diesel engine and an electric motor, then it is diesel hybrid. Similarly, if it is from a CNG source and motor, then it is CNG hybrid vehicle. And if when the energy source is a combination, when there are two energy sources, one is gasoline engine, diesel engine, and a fuel cell, then it is known as fuel cell hybrid vehicle. And going further down, for any type of hybrid electric vehicle, there are three common, rather A and B are more common. C is used only in certain cases. One is series hybrid configuration and second is parallel hybrid configuration. So let us try to look at them one by one in the next slides. So first one is, this is basically a series hybrid configuration. So again, this two parallel lines indicate the mechanical linkage between two blocks. So as you can see, there are two energy sources. One is IC engine and second is electric motor. But you can see here that in case of a series hybrid, motor is connected to the vehicle shaft. That means even if IC engine is present, IC engine is not driving the vehicle at all. It is only present for doing some other function. So in case of a series hybrid, only electric motor drives the vehicle transmission. So from this diagram, it is clear that even if since IC engine is not coupled to the vehicle transmission, it is clear that even if the IC engine is off, the vehicle is capable of moving, provided there is sufficient charge available on the battery. So what is the function of IC engine in this case? In case the vehicle is running on battery, and if the battery level goes down below the acceptable limit, then the electric motor won't be able to rotate further. In such case, this status of the battery charge, that is battery health, is communicated to the EVCU. So once the signal of battery voltage low is communicated to EVCU, then the EVCU gives on command for the IC engine to start. IC engine starts and it rotates this generator, which is mechanically coupled to the IC engine, and this energy through an IGBT based converter is given to the battery. So that means the main function of an IC engine in case of a series hybrid is to charge the battery. So on the next slides, I have mentioned advantages and disadvantages of these configurations. So I'll not talk about them over here. Let us go to the next slide. So the next slide shows what is known as parallel hybrid configuration. So as is clear from this figure, there is no electrical conversion between output of the IC engine before giving it to the motor in this case. So mechanical energy from the IC engine and mechanical output from the electric motor through a mechanical coupler directly drives the transmission. So it is clear from this diagram that for an equipment to operate, the IC engine in this case has to run continuously, which means that it is not possible, as we saw in this previous slide, it is not possible to run IC engine only at one speed. However, it has to run at different speeds depending upon the vehicular requirements. So this particular block shows a little more, some more details about series hybrid configuration. This is an engine which is coupled to the generator. Generator generates AC power, which is rectified, and it is given to the motor controller. Motor controller is nothing but AC to DC converter, or in this case, it will be DC to AC because they have shown rectifier block separately. And the motor controller drives the traction motor. Battery charging. So battery charger charges the battery, and through a DC to DC converter, it is possible to charge the battery. I'm sorry, through DC to DC converter, it is given over here. So once again, there is no direct coupling between the output of the engine and the traction motor. So now let us discuss about the advantages and disadvantages of series hybrid powertrain. So first advantage is there is no mechanical connection between the engine and the wheels. So which means that it is possible to run IC engine at one specific speed. Generally, generally IC engine is kept on, or whenever it becomes on, it runs at a particular operating point or quiescent point, which corresponds to the maximum efficiency of the engine. So that is a big advantage in case of a series hybrid. Second advantage is that the engine doesn't have to run continuously because it is required only for battery charging. So it saves a lot of emission from the vehicle. Then second advantage is electric motors have the characteristics so the second is electric motors have the characteristics which are ideal for the traction. So need of additional multi-gear transmission may be eliminated, but this is again depending upon the type of the motor. In case it is an induction motor, then induction motor may not be capable of generating the torque levels which are required by the vehicle. So it may need a multi-gear transmission in between. Control strategy is of course simpler to operate because the number of components are less. Engine can be switched off when the battery charge, which I explained in the beginning, that engine need not be on continuously. It is required only for charging the battery. Disadvantage is that energy from the engine undergoes conversion 2 times before reaching to the wheels. So I'll just go to this slide once again. So you see over here, the mechanical power is converted to electrical power, and again it is given, and again it generates mechanical power. So there is an inversion, there is a energy conversion happening 2 times. So even if the efficiencies, even though we choose components with high efficiencies, there will be 2 multiplication factors which will be less than 1, which results in reduction in efficiency. Then addition of generator adds additional weight and cost. This is the second disadvantage. Third is, as we have seen in the previous slides, motor is the only motive force which is driving the vehicle. So the motor has to be designed taking care into the acceleration and gradability requirements of the vehicle. Whereas in case of a parallel hybrid configuration, the motor is getting support from engine as well. In case the motor is not able to deliver torques in certain terrains, then engine is always available to help the motor so that they together can drive the vehicle further. However, in case of a series hybrid, that possibility does not exist. The motor has to completely take care of the vehicular motive force requirements. And another disadvantage is that if the motor shuts down, then the vehicle stops completely, because motor is connected to the vehicular shaft. So when the motor stops due to some problem, maybe under voltage from the battery or some problem in the power chain, if the motor doesn't rotate, then the vehicle comes to a grinding halt. That is the disadvantage over here. So generally, this type of configuration, series hybrid kind of configuration, is generally preferred for city applications where there are a number of starts and stops, because for each stop corresponds to regenerative braking, and the energy from the battery which is used during motoring action is replenished by braking action. So such type of configuration is generally preferred in case of city applications, whereas in case of outstation applications, especially when there is a generally preferred, because even if there is a problem with electric propulsion, engine can take over and can keep the vehicle going. So now let us move on to the parallel hybrid configuration. So parallel hybrid configuration consists of a combination of engine and motor coupled, and it drives the mechanical transmission of the vehicle. There is a provision for charging the battery as shown over here. Advantage of parallel hybrid powertrain is both the engine and electric motor can they supply torques directly. So there is no intermediate conversion required. So there is no two-time conversion required as in case of series hybrid configuration. So this tends to become a more efficient kind of configuration, at least in the long run, for longer journeys. Then the traction motor size can be smaller, because in case of a parallel hybrid configuration, the motor is supported by engine for the motive requirement. So that is why it is possible to size. I'm saying it is possible. It should not be done normally, because the vehicle has to be designed for extreme conditions. But there is a possibility that traction motor can be sized smaller. So correspondingly, there is a similar advantage for series hybrid as well. As we have seen that in case of series hybrid, engine is not coupled to the vehicular shaft. So there is a possibility that this engine can be downsized, because the requirement of the engine is only to charge the battery. So advantage of parallel hybrid is it is possible to reduce the size of the traction motor, and advantage of series hybrid is that engine can be downsized. Okay, now the disadvantage. Engine disadvantage is that the engine has to run continuously, and it has to run at different speeds as per the vehicle requirement. So it is not possible to operate engine at a single quiescent point corresponding to the maximum efficiency of the vehicle. So this is a disadvantage, and also it increases the emission from the vehicle. The structure is a little bit complicated, and hence it is difficult to control sometimes. So this particular block basically tries to indicate that it is easier to convert a serial hybrid connection to a fully electric vehicle. So this particular connection, there is a mechanical linkage between only the motor and the vehicular shaft. So this is basically a series hybrid configuration. The next developmental phase is they have added a UCAP storage or ultra capacitor storage, or maybe another additional battery over here as an additional energy source. And in the third phase, they have downsized the engine, because engine is anyway not coupled to the battery. And in the fourth phase, they have directly removed the engine and mounted only the battery modules. So over here, you can see during this 4 phases of transition, there are very little modifications which are required in the mechanical or electrical design of the vehicle. Whereas if you see the parallel vehicle configuration, then you need lot more changes. So this particular figure gives an overall block diagram of a propulsion system of a vehicle. So electric controller, which we talked about, that is EVCU, then the power converter, then power converter drives electric motor. Electric motor drives the vehicular shaft either directly or through a transmission and a differential box, of course. Now, this is a typical interface diagram, connection diagram of different constituent components of a hybrid vehicle followed by an electric vehicle as well. So over here, this is IC engine is coupled to the generator through this coupling. Generator generates electric power, but it is AC in nature, and that AC power is inverted through this inverter, which is put on the battery. This voltage level over here is mentioned as 600 to 700 volts, which is very typical of electric bus. In some cases, it is also 800 volts or so. In vehicles such as cars or auto rickshaws, it is around sometimes maybe 48 volts or maybe even lesser than that. However, the concept remains the same. Then from the battery, the power is inverted to feed the motor. This is an auxiliary inverter which takes care of the auxiliary power requirements. So in some case, so over here there are two blocks to take care of the AC as well as DC auxiliary powers as required by the vehicle. So this is DC to AC or DC to DC, and the battery communicates to the EVCU, that is electronic vehicle control unit, through battery management system and storage control over a bus, which is shown as SAE CAN, which is international standard followed for communication between the various devices. Input output is basically an interface between this is input output control box, which takes care of communication between the vehicular interface and inverter. As shown in the previous slide, I showed, if you remember, in the block diagram, I had shown one box called as DICO. So this is this block. So either this block is integrated along with the inverter, or sometimes it is kept separate for ease of maintenance. So as you can see, this is a interface diagram for a purely electric vehicle. And as you can see that the number of components are quite less. Only an inverter motor, auxiliary inverter, and the battery system, battery management system. Also, there is one component over here. It is called as brake resistor. In some cases, it so happens that due to very stringent braking requirements, sometimes it so happens that the battery is not able to take this braking energy, and it finally results in terms of tripping of the inverter, or tripping of the main inverter. So in order to dissipate that extra energy, sometimes this braking resistor is needed. It is shown as an option because it is needed only in certain cases where the braking is very fast and battery is not able to take that much energy during regeneration. Now let us talk about motors. So traditionally, as you know, that DC motors have been quite popular, though they are not used, though they are almost replaced in most of the applications by induction motors in industries. However, in certain areas like rolling mills, those are still preferred choice because of the excellent torque response. But the main disadvantage of DC machines, as you know, is the maintenance required for the commutators and the brushes. So these are not a preferred choice for electric mobility. In stepper motor, to an extent, it is not used in the main powertrain. However, it is used in some areas such as for feeding of some small mechanisms in printing machines or in robotic applications. They are preferred because of the precise control which one can have over the rotation of the motors. So general category is brushed motors and brushless motors. And apart from this one, the third one, which is quite popular, that is induction motors. Before the development of BLDC motors and PMSM motors. Induction motors were widely used in electric vehicles because of their low cost, rugged construction, good efficiency, and good durability as well. The main two shortcomings from induction motors is that induction motor efficiency is considerably low, especially during low speeds. So induction motors were not very efficient, at least during at least for the city applications where it is not possible to drive vehicles at higher speeds. And also the torque levels which are required by vehicles are sometimes higher, and you need a additional gearbox in between in order to step up the torque output from the motor so that the required torque levels for the vehicle can be reached. So these were two main shortcomings from the induction motors. So however, still in very small vehicles such as maybe two-wheelers or three-wheelers, I think they are still being used, induction motors. Now, after the development of this BLDC, basically BLDC stands for brushless. It is not a DC motor, but it is basically AC machine from AC machine with a DC mask. So it has got those advantages of DC machine. However, it is structure-wise quite different. The idea behind this BLDC machine is this was actually developed prior to development of PMSM motor, and basically it consists of a rotating part which is made up, there is no winding on this rotor. Basically, the winding is only on the stator, and this is the portion where magnets are mounted, permanent magnets are mounted, and only windings are switched at any point of time. For example, if this is R winding, Y winding, and B winding, so two windings of the motor are switched at any point of time, and the position of, and then due to the magnetic effect, the rotor rotates, and the position of the rotor is communicated to the controller through sensors. And then depending upon the position of the rotor, the next two windings are switched. So function wise, it is somewhat similar to a motor. It is not an exact stepper motor, it is not a DC motor, it is somewhat in between. It is known as BLDC motor. Now this BLDC motor has got good efficiency, and control also very good. There is low noise also. However, BLDC motors they have certain disadvantages which are listed on the next page. So BLDC motors are currently being used or proposed to be used for smaller vehicles, such as three-wheelers, for example. Now this is a block schematic of how an interface between IGBT-based converter and a BLDC motor happens. This motor is also known as trapezoidal PMSM motor, PMAC motor, because the waveforms which are communicated from the motor to the inverter are trapezoidal in shape. So it is also termed as trapezoidal PMAC motor. And so this is the stator part of the motor, this is the rotor part, and this is the feedback mechanism through Hall effect sensors. And these are the IGBTs, insulated gate bipolar transistors, which drive the stator winding. So here are the advantages and disadvantages of a BLDC motor. One advantage is, of course, it has got a better efficiency, higher efficiency. There is power consumption from the rotor is low because there is no winding on the rotor, so there are no heat losses in the motor. So cooling is better. The motor is compact. Then the maintenance is also considerably low because there is no winding on the rotor. Noise which is generated by the motor is also considerably less. However, the cost of the motor is higher. Then because of the design, because as we have seen in the previous slides, that two windings are switched at one point of time, and then the sequence follows further. So this kind of switching mechanism is difficult to handle at higher speeds. So this has limited or prohibited the use of BLDC motors for bigger applications or higher speed applications for higher vehicles. Then there is a problem of the magnets losing their magnetic effect over a period of time. That is one disadvantage. Another disadvantage is actually it is a torque ripple. Basically, as we have seen that two windings are switched at any one point of time. So in order to communicate the position of the rotor, we need three Hall effect sensors for these three windings. And so this particular switching mechanism between phases gives rise to torque ripples, especially at lower speeds. And this is one thing which increases the noise coming from the vehicle, which is not acceptable for vehicles, undesirable for the vehicles. So this is another disadvantage for the BLDC motors. Then comes the PMSM motors. The only prominent difference between a BLDC motor and a PMSM motor is that in case of a PMSM motor, all the three windings of the motor are switched simultaneously, and because of that, only one Hall effect sensor is sufficient. The drawbacks of BLDC motor, like demagnetization effect, higher cost, are also present in PMSM motors. Only advantage is that the torque ripple which is present in case of BLDC motors, especially at lower speeds, are significantly reduced, which make PMSM motors a more acceptable choice for the vehicles. So this particular table gives a comparison between trapezoidal PMAC, which means BLDC motor, and a sinusoidal PMAC or PMSM motor. Both are synchronous machines. Then the type of back EMF feedback in case of PMSM, it is sinusoidal. In case of trapezoidal, it is trapezoidal. Then continuous stator flux position variation is communicated. Here it is at every 60 degrees. Only two phases are energized at any instant of time. All three phases are energized. Torque ripple commutation is present. Here, no torque ripple or very less or acceptable, let us say acceptable level of ripple at commutation. And then the order of harmonics in the audible range are low. Here, they are lesser due to sinusoidal excitation. Then the core losses are lesser, and these have slightly higher core harmonic content present. So this gives a comparison between PMSM motors and BLDC motors. PMSM motors they are permanent magnet motors, and these are and also another advantage which I would like to mention here is they are capable of generating torques directly, and in most of the cases the gearbox stage is not required in case of this permanent magnet motors. So we can directly couple the motor shaft to the vehicle shaft in most of the cases, which reduces the complexity, which improves the efficiency.
Mr. Murli, just a small interruption. So we need to close the session maybe in 5 minutes. We are running kind of half an hour behind schedule.
Okay. I'll just quickly mention. Yeah.
Sure.
Thanks. So I'll just skip this. Actually, I'll just mention that this was a design which was previously available. This is a new design where these permanent magnets are inset into the rotor. So this kind of design is more suitable for high-speed applications. Then these are the two important parameters on which selection of powertrain components is dependent. One is the grade ability. Grade ability means the ability of the vehicle to climb gradients. So 20% of grade ability would mean that the vehicle has to rise 20 units with respect to 100 units, and this plays an important role in selection of the components. Also, the what is known as the route profile. That means what is the geography of the route, what is the gradient over how many kilometers, what is the acceleration required, what is the deceleration required, in how much time it is required, how much time is needed to complete the entire one cycle of rotation. So all these parameters are mentioned in this driving cycle, and for sizing of these components such as motor, inverter, and battery, this gradability as well as route profile must be known. Also, there are some important components, important points which are important to take care of design of the motor and inverter are: what is the maximum operating speed, what is the weight of the vehicle, that means what is the weight of the vehicle empty, what is the weight of the vehicle when loaded, what is the battery capacity, acceleration, deceleration, etc. So after giving all consideration to all the points, the design engineer plots a curve like this, which is known as traction effort curve, which shows whether whether the selected components are able to meet the requirements given by the user or not. So this particular traction y-axis, speed on the x-axis, and the gradability on the right-hand side. So here you can see there are three graphs. One is the blue colored graph, which shows the rated force. Then this dotted portion gives the power kilowatt limitation of the selected power electronics, and this gives the peak power limit, which is possible. So finally, battery design. So I'll just quickly say that currently there are different types of batteries available. This is a conventional battery, which is lead acid battery. But nowadays, lithium-ion battery, which is much more efficient, and it is possible to recycle also. Recycle means not fully, but at least most of the components. Research work is going on so that most of the components from an old battery could be used onto a new battery. Then nickel metal, but this is again under development. Ultra capacitor battery. This generally acts as an auxiliary source. Generally, ultra capacitors are not used as main source because one thing is they are extremely costly, and second is second reason. So second reason is actually the efficient. Secondly, the space requirement also sometimes it is not possible to meet properly. So in typical applications, the advantage of ultra capacitors over battery is that they are capable of delivering energy at a much faster rate as compared to a conventional lithium ion battery. So in certain cases, special cases, a combination of ultra capacitors and lithium ion batteries are used. For example, if a vehicle has to accelerate at a very rapid rate within a very within a very short span of time, then only for starting purpose, these two sources work together, and then once the vehicle reaches the required uniform speed, then this source is cut off and this takes over completely. So such are the applications of ultra capacitors. Then this shows the chemical configurations of these types of batteries, and this particular slide gives emphasizes the concept that by paralleling the battery cells, it is possible to increase the current level and voltage level being constant. In series configuration, of course, the current handling capability is equal to the individual current handling capability, but the voltage goes on adding. Then this talks about the battery management system. As we discussed in the first slide, it takes care of monitoring, then calculation of parameters, balancing, and protection. And the last one is charging solutions. So in charging also, there are different types of charging levels available. First is level 1 charging. This is normally sufficient for a shorter range up to 10 kilometers, and voltage levels are about 120 volts AC or so. So this is level 1 charging. For level 2 charging, the range slightly increases from 20 to 30 kilometers. And for both this level 1 and level 2 charging, it is possible to mount these equipments in big societies, big colonies, so that one can take their respective vehicles to the charging point, get them charged, and go. Whereas there is another charging which is fast charging or DC charging. This is generally used for bigger vehicles and for higher ranges. Only one thing one has to take care is that while charging a vehicle, one has to be sure that the battery of the vehicle is capable of taking the charging current which is delivered by the charging source. This is again quite self-explanatory. This is comparison between type 1, type 2 and DC fast charging. So only certain parameters are there. Overhead line charging is used in certain areas, but one disadvantage is that you need electric wires continuously throughout the range. This is a disadvantage actually. And last is pantograph type of charging. So buses are mounted with pantograph, and whenever then the charging lines need not be there throughout the traveling range of the vehicle. The charging can be at the start and end, and whenever there is a charging requirement, the vehicle goes to the charging station. The compressor starts, the pantograph is lifted, the vehicle gets charged, and then the pantograph comes down. This is pantograph driven. This is not here in India. It is also quietly a costly affair. as you can see, the voltage range is quite wide in case of pantograph. It is nearly equal to the voltage levels of railway, this 20 kV in the end. Then battery swapping, I think the speakers who presented before me gave an overview of this. Battery swapping is this thing where the owner can buy a vehicle without battery, and also whenever the battery loses the charge, that particular vehicle can go to the battery swapping station and exchange the discharged battery with a charged battery. This can be or it can be done automatically as well. In smaller cases, in case of two-wheelers or three-wheelers, the battery weight is quite small. It can be done manually. But in case of electric buses, due to the heavy weight of the battery, it has to be done in an automatic manner. So these are there are certain advantages, certain disadvantages over battery swapping. I think that's it from my side.
Great. Great. So, Mr. Murli, I have thoroughly enjoyed this session, and I can see clearly that you seem to love the subject a lot. So, which is why I had to interview you, because I mean, there is a lot of knowledge that you possess, and I think there are so many things that at least I personally have got to learn in this session. But there are also a lot of questions that students had, and we were, when you were speaking, there are a lot of questions which have come on the chat platform. So in the interest of time, I will not take those questions verbally, but I would request you to go through the chats and answer the questions on the chat directly, so we can move on to the next session. But I would request you to stay on and answer the queries of the students that may come on the chat platform.
Sure.
It was a thoroughly informative session, and thank you so much for taking time for the session today. It's a pleasure to have you as a speaker for the session today with us.
Thanks a lot.
Thank you, Mr. Murli. So, all right. So I understand we are running a little bit behind schedule. So we will have to skip the Q&A for this point, but we will come back again if we have time. Meanwhile, you can post your questions on the chat platform, and Mr. Murli would be answering it in written on the chat platform itself. Moving on, I am now going to invite our fourth speaker for the day, Ms. Aparna Vijay Kumar. She is going to talk about the dynamics of EV adoption. Ms. Aparna is a manager with the Sustainable Cities and Transport team at WRI. It is one of the agencies which conducts a lot of research into electric mobility in India. She supports the work on electric buses, working with agencies to aid in their transition to clean technology across India. She coordinates WRI India's engagements in Kerala with a focus on urban transport and development. She works with the stakeholders at the city, district, and the state levels to provide technical support, building capacity, shaping policy, and bringing change on ground. She has worked in the construction industry before she moved on to cities. She is a civil engineer by graduation and holds a master's degree in urban planning from the School of Planning and Architecture in New Delhi. So without much delay, I would now like to invite Ms. Aparna as our guest speaker for the next topic. Over to you, Ms. Aparna.
Thank you, Dhruv. And thank you for giving me and WRI this opportunity to be part of the conversation. We have been part of earlier trainings and sessions, and it has been a pleasure interacting with stakeholders in Andhra Pradesh. So without much ado, I'll share my screen.
We can see the screen. Yes, we can.